This is the second part of the 22nd lesson in heat transfer. In lesson 22, we have been discussing convection heat transfer in internal flows when the tube wall or duct in which the fluid is flowing is held at a constant temperature. The constant temperature boundary condition is one commonly encountered in engineering practice. One might see this boundary condition if the outside of the tube wall is subjected to a phase change, or if it is embedded into an environment in which the temperature is held fixed. By the end of lesson 22, you should be able to use a differential control volume of the flow in the tube to relate the mean temperature changes to the average heat transfer coefficient and the wall temperature. You should also be able to identify the governing equation for the mean temperature of a fluid flowing in a tube with a uniform wall temperature. That is the main goal of this lesson, to derive and identify this governing equation. As you will see, the way that the mean temperature of the flowing fluid changes in a constant temperature tube or duct is very different than how the mean temperature changes in a tube or duct subjected to a constant and uniform wall flux. On with the lesson.
Let's check our guess. So to start with, the way that I'm going to do that is I'm going to go back to this equation. And remember, this equation just came from an energy balance, from a first law of thermodynamics, right? And if you take the derivative of this equation with respect to x, okay, we're going to take the derivative of the mean temperature with respect to x. This drops out because it's a constant, and this becomes the flux times P times over m dot C sub P. Agreed? All right, so that's going to kind of be our starting place. So dTm dx is equal to the flux at the wall times P over m dot C sub P. Now, in the constant flux wall case, kind of the reason that we were able to integrate this easily is that the flux was a constant, right? And so everything on the right-hand side was a constant, and so it integrated out to be a line. In the isothermal tube wall case, that's not going to be true, right? The flux at the wall is given by Newton's law of cooling, H times Ts minus Tm, right? Which I'm going to represent as H times delta T. H times delta T. So I'm going to call that Ts minus Tm delta T. Okay, with that definition, it's kind of like I'm making a substitution. If I take the derivative of delta T with respect to x, that's like taking the derivative of the surface temperature with respect to x minus the derivative of the mean temperature with respect to x. And what's true about this in an isothermal wall case? It's zero, right? It's constant. So it doesn't change in the flow direction, like in the constant flux case, so that goes away. So I'm going to make a substitution over here. I'm going to swap out the dTm dx for the d delta t dx. So I have minus d delta t dx is equal to, and I'm going to substitute in for the flux, Newton's law of cooling. So I have h p delta t over m dot C sub P. I dropped my little hat, just know it's per unit mass. This is something I can separate. I integrate, agreed? So if I can put the d delta t over here on the left, the delta t underneath, and on the right-hand side, I have left over minus P over m dot C sub P times dx. So if I integrate this, yeah, oops, I forgot my h dx. So if I integrate this, the P over m dot C sub P is just a constant, right? The perimeter of the tube is whatever the perimeter of the tube is. The flow rate is whatever the flow rate is. The specific heat we're going to say is a constant. It's whatever it is. Okay. We're going to be integrating from the inlet to some location x. So this is like delta t at the inlet to some location x, if you want to think of it that way. And this integral of h dx, does it remind you of anything that we did before? We saw this before, right? When we integrated all the heat transfer up over a plate surface in an external flow. And we use it to define something. Do you remember what the definition of h bar was? It was 1 over x times the integral of 0 to x h dx, right? It was like, this is the average convection heat transfer coefficient that somehow accounts for all the heat transfer over that length. So notice if I multiply both sides of this equation by x, I just have, like, this basically says the integral from 0 to x of h dx is equal to h bar x. So I can make that substitution over here. Agreed? So now I have the log, because the integral of this is log delta t from delta t I to delta t o is equal to minus p x h bar over m dot c sub p. So this is delta t x. If you think of that p times x, what does this p times x really represent? Perimeter, what? It's just a surface area, right? It's the perimeter of whatever the tube is times a length up to x. This is really just like a surface area. So I have like h times a in the numerator here. Yeah. Okay, but if I just kind of write this out for delta t x, and what I have, and I take the exponent of both sides, I have delta t x over delta t I is equal to exp to the minus, h bar p x over m dot c sub p. TS is not constant, which you have to integrate for h. Well, we're still integrating for h here, David, right? Like, even we're swapping out basically the integral for the average convection heat transfer coefficient. So we did have to integrate. We did have to integrate. Okay. We're just basically taking the integral and representing it with the average convection coefficient instead. Right. Does that make sense? Okay. And then if you remember, yeah, thank you. Okay, so if you remember our definition then of the delta t, right, we said it was like Ts minus the thing. So this says Ts minus Tm at some position x over Ts minus Tm I is equal to this thing. So this is my equation for how the mass average temperature changes in the flow direction. Yeah, if you're keeping score, that's 842 in your textbook. 842 in the textbook. So we could take that and we could solve it for TMX and we could plot how the mass average temperature changes as a function of position, and it's going to be exponential, just like many of you guessed. And we'll never actually reach TS, right? We can never actually reach TS because TS minus TM is the driving force for the heat transfer. If it was 0, there'd be no heat transfer and there'd be no change in the mass average temperature, right? So we have to asymptote towards TS. We'll never actually get there. We can get close enough, but we can't measure the difference. But we're never going to actually get there. Okay, so this was kind of asking the question, what's Tm of x, right? Like, what's the equation? We got that now.